Well, good afternoon, everyone. Pleasure to be here. My name is Gustavo Rosena. I work in the SQL and Hadoop space. And today I'm going to be talking about interactive BI, more specifically about how SQL and Hadoop engines like Hive or like IBM Big SQL have evolved, and quite dramatically over the last 2-3 years from their traditional space of, let's say, batch BI, so-called reporting, into the territory of interactive BI. A few words about myself. I work off of the IBM Canada lab in Toronto, where IBM makes a number of products, including IBM Db2 and Big SQL. I worked in Db2 for over 10 years in the SQL compiler, and then I moved to Big SQL in the early days of Hadoop. Big SQL in earlier incarnations was based on MapReduce as well. So, and these days is based on Db2 technology. So we took a number of pieces of Db2 and put them on top of Hadoop to build Big SQL. On the Big SQL side, I didn't work in the compiler. I worked kind of in the other end of the stack, more on the I/O layer, the interaction with HDFS and Hive, and the integration with Spark. This is an outline of what I have for today. First, we're going to talk a little bit about interactive BI to kind of define the problem and ensure that we are all on the same page. Then I'll talk about BI accelerators, which is a bit of a niche of products that came into the market about 5-6 years ago to kind of address performance limitations of SQL engines in the area of interactive BI, obviously. And then I'm going to talk about how the technologies are really converging. So like I said in the beginning, SQL and Hadoop has made a lot of progress in the last few years, and is now playing into the interactive BI space as well. And finally, I'm going to explore the question of, can you, today in 2018, use a single engine for both use cases, the batch, traditional BI, and the interactive BI. And I will use Big SQL, obviously, as the example for that. So the process that led to this presentation was a couple of years ago. A customer came to us and said, you know what? We are using this other product, and we can execute queries in a few seconds, where in Big SQL, they run in minutes. So we were taken a bit by surprise. We take performance very seriously. We haven't been paying attention really to this space that much in Big SQL so far. So that kind of put in motion the process that led to this presentation. We had no choice but to actually go and understand what BI accelerators are and how come they managed to have such a good performance. But first, let's talk about interactive BI. What is, very quickly, it's a person that is waiting for a query response in front of a screen. That screen, the person is typically a decision maker, a business analyst, running some form of interactive dashboard, as opposed to a static dashboard. And this is a dashboard that the person can use to drill down, slice and dice data, so that there is an interaction between the person and the screen. And because of that, the response time has to be either under a second or within a few seconds. Otherwise, it breaks the thought process. So there is somebody waiting and thinking there. In the title, I mentioned SQL-based because there is a whole spectrum of interactive BI products, starting with Excel at the low end. Excel is great, it's super powerful, but it obviously doesn't scale. So the next step up, you have tools like Tableau or Click running in local mode, where you sort of copy a subset of your data into Tableau or Click. Tableau loads it in memory, and then the GUI flies. It's super fast. But again, if your data is bigger than what Tableau can accommodate in memory, it doesn't scale either. So you have to go to the Tableau live mode, which means that the person running the queries, every time they do a drill down, Tableau or Cognos or whatever they're using, that GUI is going to send SQL statements under the covers to some RDBMS that is doing all the the number crunching. That is kind of the one that we will be talking about, the sort of the GUI connected live to an RDBMS, the SQL-based Interactive BI. So let's now look at a bit of the history of evolution of interactive BI in the Hadoop space. In the beginning, there was the kind of the traditional enterprise data architecture. You had your operational data stores feeding the warehouse, possibly going into a fully normalized store, very tightly controlled. And then for performance, somebody took the work of defining a star schema on top of that, and they either implemented that in a separate database, like a Netezza or Vertica or something like that, on top of the warehouse, or maybe it's something that is within the warehouse itself. But the idea is that there is a performance layer on top that is the one that makes things interactive for the BI users, as we were seeing before. So this architecture, or small variations of it, lived for a long, long time, between 10 and 15 years, until Hadoop came into the picture, which makes things a lot more complicated. Yeah, you get all the benefits, all the ingesting sort of big data sources and doing analytics on data that didn't fit in the database before, things like that. But architecturally, things get a lot more complex. When Hadoop was introduced, it took a while until people started do SQL on it. So they first did big data workloads, and then they moved. They consider ETL. Then when SQL and Hadoop engines improved, they started doing batch BI or reporting. And at some point, somebody tried interactive BI. So it's okay. Is it mature enough for interactive BI? And the answer was obviously no. That's the red arrow over there. It was too slow for interactive BI. And at that point, something kind of funny happened. In order to get the interactive performance for BI data, what people had to do was to do a kind of a reverse offload. So they had to move data from Hadoop into the warehouse, which is kind of backwards. It's kind of an upload instead of an offload. And that is needed to get the performance. You need to put the big data in the analytic database so that you can run your interactive BI tools on top. That worked, but obviously it's super expensive because in the warehouse you pay for terabyte, so it's very expensive to upload data to the warehouse, and also it's another way of ETL, which is something you want to avoid if possible. So it's painful, and that's when BI accelerators came into the picture. So these are guys that saw the business opportunity of solving the problems that we've been sort of describing before. Say, okay, you don't have to load your Hadoop data into the warehouse. Instead, get our tool, the BI Accelerator, and we'll sort of supplement the SQL and Hadoop with the BI acceleration features that you're missing. Sometimes the BI Accelerator sits, side by side with the SQL and Hadoop, or sometimes it sits on top. We'll see some examples later on. But the idea is that you don't have to do this complicated and expensive solution to get your BI performance. What's the value proposition? Again, you can enable offloading of interactive BI to Hadoop without using Netezza or Vertica or something else. You get your fast response for analytic queries. Here you have a typical simplified analytic query. It's doing a little star schema with two tables. It's joining the two tables, grouping by one of the dimension attributes, and then doing a max on the measure in the fact table. So this is the kind of the bread and butter of what BI accelerators do. They execute this kind of queries very fast. And all of these operations are expensive on Hadoop. A join is expensive, grouping is expensive, aggregation, it's a lot of number crunching. Another feature that they have, the accelerators, is autonomics. Whenever you need to accelerate something, you need to build some data structure on the side to speed it up. That could be a materialized view, an index, a cache. There is some kind of data structure or combination on the side. And when you do that, you have to first build it, and then you have to maintain it when you get new data or you get data changes. And that is manual work, which, I mean, to some varying degrees, it's solved in some BI accelerator tools. So they do that automation for you. So a couple of years ago, when we started hearing about the BI accelerators, we say, OK, what are these guys doing that we are not doing in SQL and Hadoop? And upon closer look, what they do is always a combination of these four techniques. One is columnar storage, things like in the open source world you heard about in Parquet and ORC. There is also a good amount of caching. Cubing, or also called materialized views, or we call them materialized query tables in Big SQL, just because IBM uses 3 name acronyms for everything. And then indexing. I assume that most here is familiar with those 4 technologies, but I'm going to just run a quick example kind of to get the idea. With columnar storage, I mean, actually, with all of them, what you're saving is I/O, right? So you're reducing and reducing and reducing the amount of I/O that the engine needs to do to answer a query. So in this case, we have a table with 3 columns, ID, city, and amount. And I have a very simple analytic query, which is getting the total amount of sales in Toronto for amounts less than $500. So when you use columnar storage, the data is laid out on disk, column after column, as opposed to row after row. And that gives you a number of advantages. For example, in our query, we don't use the ID column. And that means that all the data for the ID column will not have to be retrieved from disk. So it can be skipped. The second advantage is that columnar formats, they keep statistics along with the data. So for example, over there we have an HDFS block. And there is a stat that says that all the information about the column amount, the minimum value is 603 and the maximum is 3,000. But in our query, we want amount less than 500. So when processing that query, the engine can completely skip that entire HDFS block. And then within each block, the same idea is applied recursively. So you have groups of 10,000 rows that have statistics. So let's say that in the second block, the one behind, there are rows that match our predicate. So when scanning that block, the engine will look at row groups and will be able to skip group of 10,000 rows based on the statistics for each individual group. So that's columnar. The second technique is caching. We all know about caching. The interesting part in the BI context is that there are 3 things you can cache. You can cache data, which is the most common one. But you can also cache metadata for the columnar format. This means that the next time, let's say 10 minutes later, that somebody runs a query that needs that block, I don't even need to retrieve the block if I know that the stats for that block tell me that it doesn't contain any data that I need. So that's when querying, caching stats is important. And the third form of caching is caching query results. And this is meaningful, especially in BI, because you have multiple, let's say, Tableau users that are running the same dashboard. So chances are that several of them will hit the same query at some point. Some aggregate, for example, the sales for all the branches in last month. And because you cached it, when one analyst sort of clicked on that button, maybe an analyst that clicks on the same button or a related button later on, and Tableau generates the same query, well, you'll find it in the cache. You don't have to even process the query. It's fully cached. Cubing is materialized views, so it's pre-computing aggregates, so that later on you don't need to do the aggregation every time we run the query. You just go and say, OK, do I have the aggregate for all the cities? Yes. OK, then give me the one for Toronto, and you move on, as opposed to getting all the rows from Toronto, summing all the values and computing it explicitly. And lastly, there is indexing. So like I said before, if I'm looking for Toronto and I have an index on that column, I just need to look up that specific row, which means that for that query, I can process it without scanning any data. It's all done without a combination of caching cubing and indexing. So that's the kind of games that are played to speed up BI workloads. Of course, I mean, this is nothing new. It's stuff that we've been doing in relational databases for a number of years. These are all techniques to reduce the amount of I/O. So the question is, why are SQL and Hadoop engines not using them if they are so well known? And it's just a question of timing. So the explanation is kind of based on the concept of the pyramid of needs for humans. This is the pyramid of needs for BI and Hadoop. So when you build an engine, the first thing you do is you have to get the core SQL processing right. This is quite a bit of work. Next, you want to sell your engine in the enterprise, and therefore you have to add a number of enterprise features: security, workload management, federation, high availability, a number of things. Otherwise, companies will not buy your product. Lastly, I mean, people will want to run complex concurrent workloads against your engine, so you need to be able to do resource management very efficiently. And the combination of these three things is a lot of work. It takes years to get that, I mean, to put that together in a package that really works under stress. And only then you can focus on the kind of the holy grail of of BI, which is interactive BI. So it was a question of timing. So until probably 2 years ago, SQL engines were busy with these three things, getting them right and working well together. And only starting in 2016, they started moving into interactive BI. So this is kind of a picture of that evolution. In 2014, SQL and Hadoop engines were doing some optimizations to reduce I/O. For example, cost-based optimization in the SQL optimizer, high partitioning, columnar storage that we saw before. But BI accelerators were further ahead of the curve. They were already doing sort of materialized views, caching, and indexing, and even also, I mean, taking advantage of partitioning and columnar storage. So they had that performance advantage. But now, in 2018, the landscape has changed. I don't know if you were this morning to the Hive talk on materialized views. So Hive has cubing. Well, guess what? Big SQL also introduced cubing earlier this year as well in Big SQL. And we are doing further work as we speak. In terms of caching, you probably heard about Hive LLAP, which is LLAP. It's a massive cache in memory. So with Hive LLAP, in a large cluster, Hive has probably terabytes of RAM to cache data. So they have invested massively into improving their caching technology. And it works pretty well. On indexing front, I mean, SQL and Hadoop has not caught up yet so much. I put a little bit of overlap there because there is some work. We do, for example, in Big SQL, we do indexing on materialized views. In Hive, they use Druid as a way of indexing the fact table. But this is still an area that has a lot of growth potential. So perhaps by 2020, we will see a full overlap, and we will finally get full indexing on Hadoop, which is the missing piece. So this slide is kind of a different way of presenting the same information, but it goes back to the topic of convergence in the title of the presentation. So when you look at the evolution of performance in BI accelerators, it was pretty much very good from the very start. So they started, I mean, around 2012. They did improvements, but they were already using all the right techniques for interactive BI. SQL and Hadoop, on the other hand, we started much earlier, and we did improvements, for example, with high partitioning, cost-based optimization, but each one gave us a bump, but not a complete convergence with the performance of BI accelerators. But we've seen that sort of the gap reducing over time. As I mentioned, both Hive and Big SQL now have cubing, which gave us another bump. There is on this caching, in-memory caching, and probably in the next couple of years or maybe a bit more, we'll all have indexing. Another thing that, this is more on the lighter side, but in addition to share all these techniques that I mentioned, BI accelerators also share another common trait, which is lobbying criticism against SQL and Hadoop engines. So you hear things like this when somebody wants to sell you a BI accelerator. Okay, MPP, which is the architecture that SQL and Hadoop uses, is a full scan architecture. And because of that, SQL and Hadoop is slow. They tell you you can do interactive BI on Hadoop without table scans, and we do it, they tell you. And finally, they question the scalability of SQL and Hadoop. They say that because MPP SQL engines are, well, MPP, they do not scale to many users. This, of course, is not really correct. So when an engineer on the SQL and Hadoop side hears that, they feel obliged to respond and to clarify. So MPP is really a parallel architecture. It's not a full scan architecture. So full scans in an MPP architecture are the worst case. And in most cases, they never happen. On the other hand, you do need scans, maybe not full scans, but you need to scan your columnar tables. Whenever the queries that you want to answer, you cannot answer them using cubes or caches or indexes. Sometimes you didn't pre-compute enough stuff to answer the next query. So you have to go and scan the data to find the data that you need. And finally, in terms of scalability, the SQL engines scale better than non-MPP engines. I mean, being MPP is just having more resources, having more computing power. So that gives you better scalability, not worse. So let's now look at three popular BI accelerators in the market today. The first one is it's called Jethro. There was a presentation about Jethro right before this one. And Jethro is probably the more sophisticated of the three. It's a really interesting product. Jethro is an engine, unlike the other two. It's a SQL processing engine in itself. However, it's not MPP. It's a single box. It's an SMP, which means that it uses parallelism within the box, but it doesn't parallelize across a cluster. But you can run multiple Jethros in the organization, if you like, against the same data. In terms of acceleration techniques, Jethro uses indexing, cubing, and caching. And they also have their own columnar format, which I forgot to include there. And its unique features are that it doesn't compute cubes or materialized views the expensive way bottom up, but instead they build them top down. They build little pieces of the cubes as they find that they need them, instead of sort of building an entire cube with all the values top down, which is what most other engines do. They also create indexes for all the columns. Every value in your database is indexed. But the downside of all this is that whenever you use Jethro, you have to re-ingest all of your data, all of it. They store it in their own columnar format with their own indexes. They use the Hadoop cluster, but it's not open format. It's all re-ingested into their own format. The second product that I'm going to describe is AtScale. AtScale is not an engine. Even though they do materialized views, they are not an engine. How do they do that? What they do is whenever you use AtScale, you have to go into a modeling tool, and you have to impose a star schema on top of your data. So, and then you don't query your data. What you query is the star schema that you build for AtScale. And when AtScale see these queries through your sort of view, star schema view on top, they intercept that, and they create cubes under the covers using another engine, which could be Hive, Spark SQL, or Presto. So that's what they do. They force you to use a different schema. You don't query your original schema. You query their schema. And then they use that intercepted queries to build cubes in the hope that you will rerun the same queries again in the near future. So they use cubing, caching, and another technique that they have that is not present in the other engines is approximate answers. So instead of doing brute force, for example, to compute a count distinct, which is very expensive in Hadoop, they use an algorithm called hyperlog, which can give you a very approximate answer to count distinct but it's not an exact one, but it's much faster. In terms of unique features, like I said, they impose a star schema on all of your data, and you query through their schema, not to your original data. You can also build cubes manually in at scale. So you can say, I want to have this materialized view because I know it's going to benefit me, as opposed to waiting for the system to figure that out. But, I mean, they are not an engine. They use another engine under the covers, both to build the cubes and to actually run any query. The third product is actually an open source product called Apache Kylin. Apache Kylin is, again, very different from the other two. It's, I mean, if you remember from the late 90s, early 2000s, this is really a OLAP engine, multidimensional OLAP engine. And that means that Kylin is really applying a brute force approach to BI. They build cubes sort of top down, and they sort of pre-compute the world. Of course, I mean, this assumes that you have a sizable Hadoop cluster with lots of computing resources, and they take advantage of it, which is fine. But that's their approach, is to say, OK, I'm going to pre-compute all that I can, and then when you come with a query, I'm going to look it up in all the pre-computed aggregates, as opposed to trying to execute the query. If they don't find the query in all of the cubes, they go to Hive. So they actually use 3 engines under the covers. They use Spark to build the cubes. They use HBase because, I mean, when they build the cubes, each cell in the cube becomes an HBase key value pair. And then when their optimizer realizes that they cannot answer a query with the cubes, they actually offload the query to Hive and bring the answer from Hive. So as you can see, it's 3 completely different approaches to the problem of interactive BI, which it's quite interesting. So what's the flip side of all these tools? Well, first of all, they are not general-purpose SQL engines. They just focus on the narrow interactive BI case. But furthermore, I mean, they work as long as your queries are repetitive, which means that they are generated by tools. I mean, as soon as you try to execute a query that doesn't come from a stable dashboard in production, the tool will struggle to answer it. I mean, they assume that you've trained the tool with queries that are stable over time. That's why they can struggle with unpredictable workloads or with somebody writing a SQL query on the command line. Also, if you have frequent updates or ingestion of data, the performance will be degraded because they have to keep up the updates of the caches and indices and cubes that they have built on the side. So a couple of words about Big SQL now. This is a traditional MPP SQL and Hadoop engine, very similar to Hive in terms of architecture, except that all the engine pieces, not the storage, it's mostly based on Db2 technology, so that we've developed over 20 years. Big SQL talks to the Hive metastore for metadata and to the Hadoop node. And the data is all in the open in Hadoop using ORC or Parquet or text format. Like I said, it's an MPP, so it scales very well. It has all the enterprise features coming from IBM that you would expect to handle complex, heavy workloads. It has a great cost-based optimizer, has very efficient utilization of cluster resources. That means that we can take more load than other engines gracefully in the engine. It has built-in federation for a number of relational sources like Netezza, Oracle, workload management, and high availability. On top of that, it's really deeply integrated into the platform. So it runs on HTTP. Is fully compatible with Hive. So you can create tables in Hive and query them in Big SQL and vice versa. The data is on HDFS. Security, you can use Apache Ranger. You can use the open source columnar formats. You can use Yarn for elasticity to add and remove nodes depending on your workload. You can even create tables on HBase when you have certain use cases that are not really analytic but more OLTP oriented. You can register HBase tables with Big SQL and use Big SQL as your SQL layer on top of HBase. And finally, for the more advanced sort of, not BI, but machine learning or data science stuff, we have a deep integration with Apache Spark. This slide kind of just summarizes the topic that I mentioned on cluster, on resource utilization in the cluster, a comparison with on a benchmark that we did a year and a half ago. This is on a 100 terabyte TPC-DS, which is standard Hadoop, standard way of measuring kind of the capabilities of SQL engines. And we compare against Spark using 4 concurrent streams of TPC-DS at 100 terabyte scale. You can see the elapsed time, was less than a third. CPU utilization was a bit lower, but not that much. We had a third of these reads and a ninth of these writes during the execution of the benchmark. This is kind of just to give you an idea. I will not go into all of this into all of the detail, but the materialized view capability in the current version of Big SQL. So in Big SQL, I mean, I'm going to use that star schema on the left. It's called, that's taken from a benchmark called SSB, or star schema benchmark. It's also from the TPC-D Council. So you can find that online. This graph here is to give an idea of what happens when you run sort of the star schema benchmark at factor 1,000, which is 1 terabyte, without sort of materialized views. With materialized views, you're running a single instance of the, these are, I think, 13 queries. So this is running the 13 queries single user. And this is running the 13 queries with 25 users concurrently. So this gives you an idea of how things scale with materialized views. So there are 2 types of materialized views in Big SQL. One is Hadoop materialized view, which is typically used for materializing joins. Like we see here. Here in this example, we are materializing a join between 3 of the tables, 2 dimensions and the fact table. But the interesting pieces are that you can use kind of the Hadoop acceleration technologies on the materialized views as well. So for example, you can partition your materialized view. You can sort it, and this is useful when you want to take advantage of predicate pushdown to ORC or Parquet. You want to sort your data so that there is more I/O elimination. And you can store the materialized view as ORC or Parquet files. The other kind of materialized view, we call it native materialized views, is for aggregates. So in this case, what we want to materialize, instead of materializing a join, we want to materialize an aggregation. So here, I'm materializing an aggregation over a join. And this is for tables that are lower cardinality. These tables are not stored in Hadoop. These are, because they are low cardinality, they are stored internally in the engine. That's what we call them native. And the advantage of that is that, for example, you can define indices on them. This goes back to the indexing that I was mentioning at the beginning. So you can create a materialized view on Hadoop data in Big SQL, define an index on it, and then, for example, if you run a query that has something like this, that is it's a query that is kind of the optimizer figures out, okay, I can answer this query using this view. Notice that I'm not querying the view directly. I'm just querying my original data, but the optimizer figures out that the data that it needs is in the materialized view. And because the data is, the view is indexed, like I did here, this query really becomes just a lookup on a table. So this is takes a millisecond to execute. Okay, we have some time. This is, a description of how to how using materialized view technology you can speed up a dashboard. The key thing to realize is that you have to think about when you want the interactivity with the dashboard. You want the interactivity when the business analyst is designing the dashboard, or you want the interactivity in production. And it's usually the latter. So you don't care that much about interactivity when the person is playing with the data. You care about the interactivity when the business user needs to make decisions on the dashboard running in production. And then you can play a little bit of a trick. So what you do is you prototype your, let's say that you're using Tableau. So you take a sample of the data, you bring it to Tableau, and you use that to prototype your dashboard. When the dashboard is ready, you publish it to production, and then you redirect Tableau to the production data. But something else that you do is Tableau allows you to export the SQL queries that it's using. So you can export the SQL queries, run them through an advisor or an experienced SQL developer that can create the indices and materialized views to speed up the dashboard, and then the dashboard in production is going to run pretty fast. Of course, this is not the ideal case where the tool can figure out how to do this automatically, but it's a huge step. Now you have all the tools that you need. All you need now is just an extra effort in manually creating the materialized views and the indices. But the performance, once you do that, will be truly interactive, which was the goal. Summing up, I mean, what are your options for interactive BI on Hadoop? And basically, there is no free lunch. So whatever you choose, you have to pay. If you use the analytic DB, as in the early example, you have to upload data from Hadoop into the analytic DB. That's expensive and it's painful because of the data copying and the ETL. If you bring in the BI accelerators, well, I mean, you have one more engine to tune and deal with. And also, we talk about the limitations in the use case. And finally, if you decide to use SQL on Hadoop, it has all the infrastructure there, but it still requires some manual work to put the pieces together. And to answer the question, I mean, that we posed in the abstract of the presentation, can we use a single engine for reporting an interactive BI? And the answer is probably yes. I mean, if you have the skills to make it work, today you have all the tools at your disposal. If you go with a single engine, I mean, obviously you reduce costs because you license a single product. You need skills to manage and tune a single product again. You reduce your stack complexity. You don't need to copy data between Hadoop and the BI accelerator. You don't need to duplicate this, a topic that I didn't touch on the presentation, the governance and security. When you have your BI accelerator, it's typically not integrated into security infrastructure, so you have to duplicate all the security on both sides. And finally, you have a single vendor for service support. If you have two vendors that are whose products are working together, it's very common for problems not to be clearly on one side or the other. So it's when you have a single vendor that you can call for a problem, you get much faster resolution. And here on the right, I mean, these are all topics that I've touched on the early part of the presentation, which are the pros and cons of an engine, a SQL engine like Big SQL, and BI accelerators when running interactive BI on Hadoop. And that's pretty much all I have. So to conclude, we've seen that modern SQL and Hadoop engines, they now have all the same techniques that you find in BI accelerators, such as cubing, indexing, caching, and even more. They can do interactive BI. There is nothing wrong with MPP. It's just more computing power. I hope that now you have a better idea of how BI accelerators work and what are the trade-offs compared to a SQL engine. And finally, SQL on Hadoop still has work to do, for example, in indexing and automation, but it's evolving pretty fast. Thank you very much.